are discussing the propagation of electromagnetic waves in anisotropic media, and in the last section we have discussed how we can represent the direction of propagation of the electromagnetic waves when it is given, then to determine the wave refractive indices and the direction of the d vectors. So, we will make use of that characteristic equation to solve the direction of the d vectors as well as the wave refractive indices. So, the direction of the d vectors, which are the direction of the polarization, that we will discuss in this connection. Then we will consider two example cases. One is along the direction of propagation of the electromagnetic waves in the z direction, which is a simple case, and then slightly different case when the electromagnetic wave is propagating in the x z plane. So, we have seen this characteristic equation, that is an equation which has a similar diagonal elements and similar off diagonal elements connected with this E x, E y and E z equal to 0. So, this matrix, the determinant value of this matrix will be equal to 0 for the non trivial solution for this n omega square, the refractive indices of associated with the wave. So, now we will consider the propagation of the wave along the z direction. So, given the direction of propagation, that is along the z direction, now we will see how this determinant equation simplifies by plugging in the properties of the values of k x, k y and k z. Then we will look at the quadratic equation, which is a result of this determinant, and the solution of the quadratic equation, that is the two values of n omega, the wave refractive indices. Then knowing that, how we can extract the electric field direction from there. So, and then thereafter we will also discuss the case of the wave which is propagating along the z x direction. So, when the wave is propagating along z direction, then you have k z is equal to 1, the only component which survives, because there is no component k x or the component k y, both put equal to 0. Therefore, so the wave is travelling in the z direction. If you look at the schematic representation of the wave propagation. So, we use these values k x equal to 0, k y equal to 0, but k z equal to 1. This equation will take the shape of this, because k x equal to 0. So, this will make this quantity, this term 0, this term also 0, k x will make this term 0, k x will make this term 0, k y will make this term 0. So, 1, 2, 3 plus 3. So, all 6 of diagonal terms will be equal to 0. So, you have a determinant now for this case, that is the case of wave propagating along the z direction, which will look like this, that the diagonal elements of the determinant will be put equal to 0. So, from this equation, if I open the bracket, then I can write in this form this quantity into this minus 0 will be equal to 0. So, I have done that 1 by n omega square k x minus 1 into 1 by n omega square k y minus 1 into 1 by n omega square k z equal to 0. Because this quantity does not have any minus 1. So, this into this into this, the product of these three quantities. So, if you now multiply these, this will yield 2 roots of n omega, which will be n omega, because anyway this quantity will be put equal to 0, or this quantity will be equal to 0, or this will be equal to 0. But in any case n omega is not 0 in general, because we are looking for a finite value solution, and k z cannot be 0. So, this quantity cannot be 0. So, either this is equal to 0 or this bracketed quantity will be equal to 0. So, this the first one yields that the value of n omega must be equal to under root of k x, and from the second one we find that the value of n omega 2 will be under root of k y. So, we have two wave refractive indices for the case of wave propagating in the z direction, and the wave is propagating in the z direction. The refractive indices that is seen by the wave is under root of k x and under root of k y. So, simply it indicates that the refractive indices are associated with the permittivity of the medium along x direction and along y direction. The wave is propagating along the z direction. So, the eigenvalues n omega 1 and n omega 2, these two values are the two refractive indices seen by such a wave which is travelling along the z direction, and the corresponding waves that represent, that sees the refractive indices values of this and this are the two directions of the polarizations. The two wave refractive indices depend on the relative permittivities along x and along y. So, the wave is along z direction, but the refractive indices are due to x and y direction. So, this is very interesting. So, substituting the value of n omega 1 equal to this and n omega 2 equal to this in the eigenvalue equation, we can find out the respective eigenvectors E x, E y and E z. So, this discussion is very interesting to know that given the refractive indices, then how we can obtain, we can find out the eigenvectors, that is the direction of the E x, E y or E z, whichever is surviving, and those directions will be called the polarization directions. So, by knowing the refractive indices, we can calculate the direction of the electric fields, and hence we can also calculate the direction of polarization of the wave when the direction of propagation of the wave is given. So, let us first use the value of n omega 1 equal to the under root of k of x, that is the permittivity along the x direction. So, if we use this value in the second eigenvalue equation, remember that second eigenvalue equation looked like this. So, k y, k x, E x, but out of this, because k x and k y are 0, so this quantity will become 0. So, 0 into E x, but now k x square is also 0. So, this minus k z square, k z square is equal to 1. So, this minus 1. So, I have written exactly that, but n omega square I have used the value of n omega 1. So, that is equal to 1 by k x into k y minus 1 into E y equal to 0, and for the third term, since k y equal to 0, so we have 0 into E z equal to 0. So, this is the reduced form of the first equation, where we have used the appropriate values of k x, k y, k z, and also the n omega 1, the value of the n omega. Then only this quantity has to be 0. If it is so, because k x and k y in general they are not equal, that means E y must be equal to 0. So, let us understand this situation, that a wave is travelling along z direction and it sees a refractive index which corresponds to the permittivity along the x direction, then the field E y is not there, and because it is propagating along the z direction. So, therefore, E z is also not there, we will see that. So, the only possibility is that U I is not equal, E x is not equal to 0. So, this the consequence of n omega 1 is equal to under root of k x, the permittivity along the x direction is that U I cannot be existing. So, U I must be equal to 0. So, the wave is travelling along the z direction, the refractive index seen by this wave is n x and there is no U I. So, it is only the E x which is surviving. So, let us use this refractive index values, the wave refractive index values when we plug in to the third equation. Again this quantity is equal to 0 because k x equal to 0, k y is also equal to 0. So, this is equal to 0. So, 0 into E x, 0 into E y, and here this quantity and this quantity both of them are equal to 0. So, if we write this equation, we get 0 into E x, 0 into E y plus 1 by k x k z E z equal to 0. That means k z by k x into E z equal to 0. It simply tells you that because k z and k x, they are whatever might be the value of this, they cannot be 0. So, E z must be 0. So, for a wave we have seen two consequences, one is E y cannot be 0, E z cannot be 0, the wave is travelling along the z direction. So, the only possibility is E x not equal to 0. Let us see that when I use the first equation and I use the same refractive index values, a wave refractive index, then because this quantity is equal to 0, this is also equal to 0 and this is equal to 0. So, in the same way we can write this equation that k x by k x minus 1 E x 0 into E y plus 0 into E z equal to 0. As a result, this quantity, because this is 1 minus 1 equal to 0. So, 0 into E x is equal to 0. That means E x not equal to 0. So, therefore, for a wave which is travelling along z direction, I find that the refractive index seen by this, the wave refractive index seen by this wave is due to the electric field which is along the x direction, and the value of the refractive index is due to the permittivity value of the medium along the x direction. So, the second equation gives E y equal to 0, third equation gives E z equal to 0 and the first equation gives E x not equal to 0. So, you have only E x associated with the wave which is travelling along z direction if the solution you assume is due to the permittivity along, due to the refractive index seen by the wave along the x direction. So, such a wave is called x polarized because the displacement vector or the electric field vector, they are along the same, along this direction. For the wave having refractive index n omega 2 is equal to under root of k y, that is if I use the other solution, that is the other root, then and if we proceed in the same way, that is k x is equal to k y equal to 0, this quantity becomes 0, we can write 0 into E x, and similarly this quantity is 0, but this is equal to 1. So, we can write k y upon k y minus 1 into E y, and for this quantity because k y equal to 0, we can write 0 into E z equal to 0. It simply means that this quantity 1 minus 1 which is equal to 0 into E y equal to 0, that means E y cannot be 0. We can use the refractive index value in the other two equations, that is equation 1 and equation 2, to identify that in such a situation it is only U I that is not equal to 0, but E x and E z they are equal to 0. So, when you consider the property, when you consider the solution for the wave refractive index n omega 2 is due to the permittivity along the y direction, then it is only the y field, y electric field that survives, and the propagation is along the z direction. So, the refractive index n omega 2 equal to q y, it gives you a y polarized light. So, we can now find out that when the wave is travelling along the z direction, this wave can see a refractive index, wave refractive index, which is along the x direction and given by this permittivity square root, and the electric field is along this x direction. This wave can have, because it has two solutions, this wave can have a refractive index value associated with it is n omega equal to under root of k y, and the electric field is directed along the E y. So, this wave which is travelling along z direction can have two polarizations, that is E x and E y, and the corresponding refractive indices n omega 1 and n omega 2 are given by these two equations. So, when the wave is travelling in the z direction with the electric field E x, that is, this is the x polarized wave and this is the y polarized wave. So, there are two possible polarizations associated with the wave which is travelling along a direction z. And now, we will consider the other situation, that is when the wave is travelling in a general direction in the x z plane, that is, it makes an angle of psi equal to theta plus phi, where theta is the angle of the angle that the pointing vector makes with the z axis, and phi is the angle that the direction, the ray direction and the wave direction they make with each other. That is, the wave direction is given by k vector, whereas the ray vector, the ray direction, that is the pointing vector, is given by s. So, this angle is phi, the same notation that we have used earlier. So, in this case, when the wave is propagating along x z plane, we can write that, because this is your k vector, we can decompose the vector along the z direction, this is the angle psi. So, k z will be equal to cosine psi and k x will be equal to sin psi. So, now we will use the value of k x and k y and k z in the eigenvalue equation, that is the determinant equation. So, if I do that, this k x, k y and k z we plug in to this equation, then it will take these values, that 1 by n omega square k x, capital K x minus cosine square psi 0 sin psi cosine psi, and similarly this you can see that the diagonal elements which are almost symmetric, this x x component and z z component, they are the same, but thus y y component is slightly different, because this k z and k x they are having the values, whereas k y is 0. So, from this determinant equation, if you open up this determinant, we can write this equation in this form, this into this minus 0. So, that is what I have written, k x by n omega square minus cosine square psi, and this. So, this into this I have written, and there will be one more value, that is for this into this. So, we can write this equation, because k x by n omega square, no, k y by n omega square minus 1 and k y by n omega square minus 1, it appears in both the terms. So, I take them out and we put these remaining quantities in the bracket. that is kx by n omega square minus cosine square psi, and this remaining part of this equation, that is sin square psi cosine square psi equal to 0. So, this reduced equation, if I simplify, then if I simplify this equation, that is I again multiply this, it will give you cosine square and sin square product, which will cancel because you have minus and minus will give you plus. So, sin square psi and cosine square psi will identically vanish. There will be only x by n omega square sin psi, k z by n omega square cosine psi with minus sign multiplied by this quantity. So, that is what it appears, that k y by n omega square minus 1 into this quantity is equal to 0. So, we get an equation which involves k x and k z, because the wave is travelling in the x z plane. So, 1 by n omega square k y by n omega square minus 1, this quantity could be 0 or this quantity could be as well 0. So, we have two different possibilities. The possibility that this quantity will be equal to 0 will give you a solution for n omega, that is k y by n omega square minus 1 is equal to 0. This will give you simply a solution that n omega 1 equal to k y. We will see what does it mean, and in the case of this quantity becoming 0, we will see that n omega square 1 by n omega square will be equal to cosine square psi by k x plus sin square psi by k z. It is not simply the vector sum or the sum of the square root of the permittivities, but it enters into this equation in a very specific way in terms of cosine square psi and sin square psi. So, the second root depends on k x and k y, which involves the sin square and cosine square function of the angle that the wave makes with the ray direction in general in the x z plane. So, by doing this, we have seen that there are two eigenvalues attached with this wave which is propagating in the x z plane. These are n omega 1 and n omega 2, and these two values are the two refractive indices seen by the wave. Corresponding to these two waves that is propagating along x z plane, there are two different relative permittivities corresponding to x and x and z directions. So, let us see that when you substitute this n omega 1 and n omega 2, these two values, the two solutions of the determinant equation in the eigenvalue equation, then we can find that n omega 1 is equal to this and n omega 2 is equal to this quantity. So, these are the two respective eigenvalues for the wave which is propagating in the x z plane, and the eigenvectors corresponding to these will be E x, E y and E z, which can also be found out by the same way we have done it for the z propagating wave. Hence, the polarization directions can also be determined by knowing the solutions n omega 1 and n omega 2. Let us try to look into that for the wave with refractive index n omega 1, that is the permittivity due to the y axis along the y axis of the medium. Then if I use this solution in the second equation, you remember the second equation. So, we will get 0 into E x, 0 into E x, because this equation itself is 0 and you have E x outside. This quantity into U y will be surviving, and this is 0 into E z is equal to 0. So, in the second equation I have used the value of 1 by n omega square is equal to 1 by k y. That directly tells you that k y by k y minus 1 into u y equal to 0. So, if this quantity is 0, so y cannot be 0, the wave is y polarized. That means, when the wave sees a refractive index which is due to the refractive index of the medium along the y axis. So, then u y field exists. So, u y field, it is the direction of the electric field that decides the refractive index of the medium that is seen by the wave when travelling along that medium. So, this wave u y, which has a corresponding refractive index n omega 1, is y polarized. So, for one solution of this wave is very straightforward, that is when the refractive index is n omega 1 equal to under root k y, then the wave is y polarized, and it sees the refractive index k y and it makes an angle. So, the other polarization will be this, even though the wave is travelling along this direction, the direction of polarization, the direction of the electric field vector is along the y z plane, and it is pointing along the y direction, and the value of the refractive index is square root of k y. Now, for the second solution, that is 1 by n omega square is equal to this. If I now substitute into the first equation, you can see that this equation into E x, second term is itself is 0 into u I, and third term you have this. So, if you arrange this equation sin x cosine x into E z equal to this into E x. So, E z by E x into sin x cosine x, you can see that this quantity identically vanishes when you use the value of 1 by n omega square equal to this. So, they will vanish. Therefore, for this value of the refractive index, we find that E z by E x sin x equal to this, and E z E x by k z E x equal to tan psi. So, it means that this quantity is the component of the dielectric displacement vector along the z direction, and this is the component of the displacement vector along the x direction. So, they are inclined to each other at an angle of minus tan psi, which is an interesting finding. So, you can see that when the wave is, if you consider the solution, the second solution, that is 1 by n omega square 2, this solution will give you a polarization where the electric field vector, the displacement vector, lies in general in the x z plane, and the dz and dx, if you decompose this into two components dx and dz, this will be dz. So, because it will be directed in the negative direction of the z. So, dx by dz will give you this value of minus tan psi. So, the displacement vectors are inclined at an angle of psi with the direction of propagation of the wave. So, for y polarized wave, you have a very specific case that it is directed along the y direction, but for the other polarization which is in the x z plane. So, the yellow circles and this arrows, they denote the two polarizations corresponding to the two refractive indices seen by this wave. So, there is a checkpoint that if you take psi equal to 0, then you can get this quantity equal to 1, this is equal to 0. So, n omega 2 becomes exactly this. So, that means if you take that wave is propagating along z direction, you end up with the earlier possibilities that the two polarizations are along x and y direction, and these are the two refractive indices. And if you put psi equal to pi by 2, that is the wave is now travelling along the x direction, then putting this value, this quantity will become 0. So, you will end up with n omega 2 equal to under root of k z, n omega 1 equal to under root of k y, and again you will get these two polarizations which are the eigenpolarization, that is, it is along the z direction, another is along the y direction. So, these are the two different polarizations. So, by doing this we could actually identify that what will be the direction of polarization, what are the direction of the electric field vectors, and a slightly different situation when the wave is travelling along the xz plane, what are the two different directions of the polarizations. So, in the next section we will continue with this. Thank you.